Are we recording yet? Or okay, so
yes, we are.
Let's continue. Okay, so now it's officially the beginning. It's my pleasure to welcome Leszek Kołodziejczyk from Warsaw, who will speak again at MOPA here, and this time about an isomorphism theorem for models of weak Kőnig's lemma without induction. Welcome, Leszek.
Thanks very much, Roman. As you can see, this is joint work with Marta Fiori-Carones, who is well, officially in Warsaw, physically in Italy, and at the seminar right now. Lawrence Wong from Singapore, and Keita Yokoyama from JAIST in Japan. I guess for this seminar, I felt that I can start with the definitions, that this audience is technical enough that I don't have to discuss the motivation first, although I will say something about the motivation, but just go through the definitions and notation that we'll be using. We'll be talking about theories of second-order arithmetic. So we have a two-sorted language with first-order variables for the natural numbers, which will be denoted by lowercase letters as usual, and second-order variables, which will be uppercase for sets of natural numbers. The non-logical symbols are the usual arithmetical symbols on the first-order sort, and then we have a membership relation between a first-order and a second-order element. I'll use this notational convention that I guess merges a few conventions from second and first-order arithmetic in particular. So if I use notation like sigma 0n, that means the first-order quantifier alternation class, but with second-order quantifiers parameters allowed. Sorry. So no second-order quantifiers, but second-order parameters are fine. If I want a purely first-order, or if you will, light phase formula, I will just write sigma n or pi n without the superscript. So a missing superscript means it's purely first-order. If I want to list the parameters, the second-order parameters explicitly, I will just use the notation without the superscript, but with a list of the parameters after the sigma n. The theories we'll talk about today will be mostly extensions of this sort of weaker, maybe less familiar base theory for reverse mathematics, which is known as RC0 star. So this is sigma 1 collection. You don't have, or delta 1 induction if you prefer. It's the same thing in this context. We don't have sigma 1 induction, so it's sigma 1 collection, delta 0 induction, of course. We have totality of exponentiation as an axiom, or you can have the exponential function as an extra symbol in the language, doesn't matter too much. And we have delta 1 comprehension. So we have comprehension for recursive sets, possibly with things that are already known to be parameters. This theory is conservative. It's fully conservative over B sigma 1 plus x. So its first order part is sigma 1 collection plus x. The usual base theory used that the people in reverse mathematics use adds sigma 0 1 induction on top of that. So we have induction for properties that are recursively enumerable relative to whatever other sets you might already have in your second-order universe. That theory is called RC0. RCA stands for recursive comprehension axiom. And the first-order part of RC0 is I sigma 1.
Leszku,
So this is hopefully a sort of reminder or review.
Leszku, can I ask a quick question?
Yes.
So there is this sigma 1.
Sure.
There is sigma 1 collection here, which I didn't recall from the
Right.
last presentations. What is sigma 1 collection doing here?
What is sigma 1 collection doing here? Well, it's being an axiom, but perhaps I just had delta 0 induction. That's possible. There is no difference. Namely, if you've got delta 1 comprehension and very minimal amounts of induction, bounded induction with parameters suffices, more than suffices, then you get delta 1 induction, okay? Because you've got induction relative to every set. And everything that's delta 1 is a set, okay? So we get delta 1 induction, and delta 1 induction over X at least is known to be equivalent to sigma 1 collection.
Oh, I see. All right.
Okay, so I might have not had sigma 1 collection here, previously that's possible, but these things are equivalent. This theory does prove sigma 1 collection definitely.
All right, thank you.
Relative to all set parameters. Okay, thanks. Thanks for the questions. If you have anything, if you have any questions, by the way, do interrupt me. That's the best way, I think, to interact. So our main interest in this talk will be models of this weaker theory, RC0 star, that aren't models of the stronger theory. They're not models of RC0. So they don't satisfy sigma 0 induction. Each such model, if you think about it, has some sort of violation of sigma 1 induction. What that means is that there is a proper sigma 1 definable cut, again, possibly with some set parameters used in this definition. Let's call the cut I. And the cut I also enumerates in increasing order some bounded definable, therefore available as a set via comprehension. The cut enumerates some set in the second order universe. So a model of recursive comprehension with failure of sigma 1 induction is this sort of thing. There's a standard part, of course. The model is going to be non-standard because we're violating some form of induction. And then there's this cut I, which might be standard, might not be. And then somewhere there is in the second order part, there is a set, let's call it A, that can be enumerated as A0, A1, A2, and so on for AI in this cut I. So that's something that's always true for these models of not I sigma 1. This picture also introduces a convention that I'm kind of used to by now. I'm not sure how often we'll have to use it, but maybe a few times. So Blackboard N stands for what the models or theories believe to be the natural numbers. Omega stands for the standard natural numbers as a cut in a non-standard model, for example. Okay. There's one technical thing that I will be sometimes taking advantage of. This is purely technical, but it is in fact true. We checked this once upon a time. Namely, in a model of I delta 0 plus x, where sigma 1 induction fails, there's not just a sigma 1 definable proper cut. There is one that's closed under x. That's something that Keita and I verified in a paper, in the first paper we published together, something like 5 years ago. But I guess it's pretty easy, so it might have been known earlier as well. I don't really know. Okay, so these are the models we'd be interested in. Now, here comes the motivation. So what was our motivation for this? We mainly had two bits of motivation. So one was that a certain problem of Henry Towser that I've been interested for a number of years, and some of you know it. I'm sure that I talked to at least Roman and Ali about this problem. Namely, Towser proved that if you consider pi1-2 sentences and think of their pi1-1 conservativity over an induction principle as a decision problem, given a pi1-2 sentence, is it pi1-1 conservative over a certain amount of induction on top of RC0? Then that problem is pi2 complete. It's as complicated as a conservativity problem can be for recursively axiomatized theories. So that's something that he proved using a nice forcing argument. And he asked, well, he was working over RC0, so the question only really made sense for n equals 2 and beyond, whether the same holds if you replace I sigma n with B sigma n. So he asked whether if you take, say, RC0 star, let's generalize the question to n equals 1 as well. If you take RC0 star plus B sigma n and ask yourself, well, given the pi1-2 sentence, is it pi1-1 conservative over this theory with B instead of I here? Whether that's still pi2 complete as a computational problem. So that was one piece of our motivation. The other piece might have been others as well, but these are the two main ones I'm aware of. The other piece was that there are a number of interesting problems in reverse mathematics concerning the, say, proof theoretic and computational, whatever else, strength, but especially proof theoretic strength or more generally logical strength of various statements from combinatorics, mainly from Ramsey theory, most prominently Ramsey theorem for pairs and two colors. And the problems that are left in that area, many of them are about understanding the behavior of various combinatorial principles over RC0 plus sigma 2 collection plus the negation of sigma 2 induction. So there are some principles, in particular Ramsey theorem for pairs itself, where we understand what's going on over I sigma 2. They imply B sigma 2, so nothing interesting happens below B sigma 2. And the remaining piece of the puzzle is to understand what happens between B sigma 2 and I sigma 2. So people care about that. And if you go like one level down in the arithmetical hierarchy, that's going to be RC0 star plus B sigma 1, which is contained in the theory as mentioned, plus null I sigma 1. So we're kind of trying to understand this pretty complicated set of questions about the strength of Ramsey's theorem, which are largely about B sigma 2 and null I sigma 2, by looking at models of B sigma 1 plus null I sigma 1. So we're trying to understand collection and null induction models at a level below the one that people in reverse mathematics care about. Yeah, so these are our two pieces of motivation, and we wanted to understand what sort of constructions you can do over in the setting. So RC0 and null sigma 1 induction. One classical construction that's known to be doable and has been for a pretty long time relates to weak Kőnig's lemma. So just as a reminder, I'm assuming that all or most of you know this, but weak Kőnig's lemma is this principle that says every infinite binary tree where binary is syntactically binary, meaning its nodes have to be 0-1 strings, finite 0-1 strings with the sons of a node being obtained by adding a 0 or a 1 at the end. So weak Kőnig's lemma says that every infinite binary tree in this sense has an infinite path. If you add this principle to RC0 star, you get WKL0 star. If you add it to RC0 without this star, you get WKL0 without this star. Okay, so this is a pretty important principle. It proves much more mathematics in the sense of reverse mathematics than RC0 does itself. But importantly, it's pi11 conservative. In particular, it has no new arithmetical consequences in both settings, both in the presence of sigma 1 induction and the absence of it. Over RC0, so with sigma 1 induction, this was proved, I guess, by Harrington, supposedly in 1977, but I think the first published proof is in Simpson's book, Subsystems of Second Order Arithmetic. The result for over sigma 1 collection was actually published earlier, I believe, but it was obtained later. It's in this Simpson-Smith paper that introduced the theory RC0 star.
Let's go.
Yes.
Since we're talking about history, I always say on the situations that the first theorem, the Harrington theorem, was also proved by Zygmunt at almost the same time. He's never published, but it was in the abstracts of the
logic colloquium. Yeah, I guess I should probably be mentioning that for nationalist reasons, if no others.
Yes, and that's why I am doing this. But also
that's very good. I mean, I appreciate that. So I saw this abstract in the logic colloquium abstract book once upon a time, but I would not be able to give you the references off the top of my head. So Roman, if you can send it to me after the seminar at some point.
I have all those references at home that are not in.
Yeah, I mean, there's no rush, but I guess I should mention this every other talk I make on this topic.
Right, no, because I also have Zygmunt's handwritten notes with the proof, and it's interesting that Zygmunt's proof is very much like Harrington's.
Yeah, it's kind of natural. I mean, you can do it in a different way. So the classical proof, both for Harrington's theorem and for Simpson-Smith, is a forcing argument. The point is you keep adding paths in trees by forcing, and the way you force is you take your tree and your forcing conditions are infinite subtrees of the tree that live in the ground model. So the conditions are for a given tree T, and you want to add a path in T, are subtrees of T that live in the second order part X of the ground model, but that remain infinite. And in the end, the generic is a path. You can do this proof in a different way. For instance, you can prove it using end extensions. I think Lawrence has actually published this. So there is a very, very close connection between expansions of models of B sigma 1 and end extensions.
Wasn't it Lawrence and Ali?
It might be possibly either or both. I mean, there's a long paper by Lawrence and Ali about the model theory of WK to 0 star, and there's a short paper of Lawrence that brings up a few issues concerning that, proves some sort of proof non-speed-up result for weak Kőnig's lemma, using this sort of argument. I guess Ali is in the audience, right? So Ali, you could actually remind me.
Actually, I'm 99% sure that our paper does not have an alternative proof.
So that's why I was thinking that it's this short paper of Lawrence's, or maybe it's something else. You shouldn't trust me on the history too much.
I think our paper, as you pointed out, does have an alternative proof of the Paris-Wilkie theorem that models of ideal to 0 plus x plus b sigma 1 can be end extended.
The expansion versus end extension connection is certainly worked out in your paper.
Right.
Theorems I would reference for this topic. Not so sure about the reproof of Smith-Simpson, for example, but never mind. Or of Harrington. But there's definitely an argument that you can do using end extensions, and if you set it up in the right way. Anyhow, this is something that you can do. And then we started thinking about what else you can do. And, in the process of thinking about these models of B sigma 1 and not I sigma 1, and X, of course, we noticed two main things. That some of this was like simply classical and known, but we only learned about it on the way. Some of it we I guess discovered, either rediscovered, or maybe some of the stuff is we discovered for the first time. So there are two prominent to me features of these guys, of models of sigma 1 collection, not sigma 1 induction. Firstly, they have lots of automorphisms. I guess the definitive result here is due to like a tandem of Roman and Richard K. I mean, I think Roman first stated it, and then K pointed out some issue with the proof and had a reproof, and Roman had an errata for the proof. But there was earlier work by various people. I mean, some of you might have been among this.
Right. No, this is I think this is quite correct what you're saying. But I just want to add something to it, because Peter Claude has joined us today for the first time, and I was visiting Peter either in 1988 or 1989 in Boston, and I was talking to him about these constructions.
Okay, so I may actually be missing some people who should be credited here. Even some of the names I just put on here due to Lawrence's knowledge, so I apologize if I missed somebody. Yeah. But anyway, the point is that one prominent feature of these guys is that they have lots of automorphisms. So this is not maybe the most definitive statement, but for instance, if you have a large enough cut, let's say it contains a sigma 1 definable proper cut, and if this cut is closed under X, then there's going to be an automorphism which fixes all elements in that cut and moves an element below each element above the cut. So for every large enough cut that's closed under the exponential function, there's going to be an automorphism for which this is the initial segment of fixed points. And you can also, put some extra constraints on the automorphism. You want to, keep a fixed finite tuple in place and move something below some other point, and so on. So these things have lots of automorphisms. They're very non-rigid in this way, as opposed to some models of sigma 1 induction, right? For instance, the sigma 2 pointwise definable model. So many models of sigma 1 induction and not sigma 2 collection, they can be kind of rigid. These guys are not. But it turns out that they're sort of rigid in a different sense. They're hard to expand. So in the process of trying to kind of reprove Towser's result for collection, Towser's proof went by expanding models. We tried to see what you can do, what sort of things you can satisfy by adding sets to second order parts of these guys, and we were failing at each step basically. So first you realize that this tree forcing that preserves B sigma 1, the sort of forcing that Harrington used, and that I check, I guess. But other typical forcing notions don't work. So Cohen forcing doesn't preserve B sigma 1 in general, nor does Mathias forcing. Something that Lawrence noticed at a certain point was that you cannot also, once you have a sigma 1 definable proper cut, you cannot expand to add new sigma 1 definable cuts and still keep sigma 1 collection. So if you get new cuts, new definable cuts, you're necessarily losing a collection. So that was pretty remarkable. And a similar construction also shows that you cannot really get sparser cofinal or infinite sets in the second order part than the ones you already have in your ground model. So this is completely false over RC0, say, where if your second order part is the decidable sets, for instance, at the beginning, then you can add a set whose canonical function or whatever it's called grows much faster than any computable function. So you can add a set, I guess it's called hyperimmune or something, which is in some sense much sparser than any of the decidable sets. This is no longer true over not I sigma 1. So lots of stuff cannot happen by expansion. And eventually we started wondering whether there is some reason behind one or two or both. And I guess we have something that's pretty much can be considered as something like a joint explanation of both these things and more. So here's a theorem. Here's the main theorem I wanted to discuss. Namely, if you get a model of weak Kőnig's lemma, if you get two models of weak Kőnig's lemma, countable models, meaning the sets there are countably many sets as well in each case. Let's say MX and MW. And both of these guys not only share the same first order universe, but they share a common counterexample to sigma 1 induction. So there's some set A in both the second order universes that violates sigma 1 induction. So then the models are actually isomorphic. To me, this was pretty stunning. And we only got to this result in various steps in which kind of strained our credulity more than once. But yeah, it seems to work, and it's true, I believe. And that's what it seems we get. So at some point we had a version in which one of the two had to be a coded submodel of the other. At some point we required saturation, but right now I think you don't. So basically, if you've got two models that share a first order universe and a counterexample to sigma 1 induction, and they're both models of weak Kőnig's lemma, then they're isomorphic, assuming compatibility, of course. So firstly, this recovers the many automorphisms result because
sorry, may I interrupt you? Because
sure.
The most interesting case is this B sigma 2 plus not I sigma 2. So is this theorem literally true if I erase star and substitute 2 instead of 1?
I do not know. I doubt it. I will tell you what is true towards the end of the talk. I will tell you what version of it holds using the same sort of argument. And I do agree that it's interesting on the level of n equals 2 as well. But for now, we don't have strong reasons to believe that you can literally, replace 1 by 2 in the statement in RC0 and the star and drop the star. But for just weak Kőnig's lemma, this has to be false, I think. I'm pretty sure that this has to be false. If you just take weak Kőnig's lemma, and I was thinking of this principle that plays the role of weak Kőnig's lemma at the level of delta 2 sets, which is called COH, the cohesiveness principle. But for weak Kőnig's lemma, this is bound to be false. There's so many Scott sets that behave in the standard model that can be kind of imitated at the level of I sigma 1 already, that I am strongly inclined to believe that this is provably false. I'll tell you what you do get using this method, okay, later on. So coming back to what follows from this on a kind of bird's eye view level, on a big picture level. Firstly, since a model will have many weak Kőnig's lemma structures on it, and they all have to be isomorphic, then the isomorphisms of these models will induce automorphisms of the first order part. And these will be, well, first of all, they will move the first order part around quite a bit because they have to in order to, get these second order parts set up, right? So they'll mix and match these first order elements. Yes.
So I got a question I didn't have a chance to think about, but you have this assumption that there is this A that's in the common part of X and W. Do you know when it happens? Does it have to happen?
Does what have to happen?
Well, could they have those sets that falsify sigma 1 induction in separately, not in the common part?
Could they have that and be different? I believe so. So I think you can have this situation where you can take a model. I would have to check some, unpublished notes of Lawrence or ask Lawrence directly. He might be relying on somebody, possibly Jim Schmirl's results. So maybe Jim will know. But there are some results. I would not know whom to credit them for them. That you can have a model of a pretty strong theory, I guess sigma 1, well, maybe PA or something like that, and expand it in two different ways to be sigma 1 and not I sigma 1. So you can have two different families of sigma 1 definable cuts. Mm-hmm. And those guys will not, I guess well, I don't know, the first order parts might actually be I don't know. The statement may still be true, but it can happen, I think, in principle, that you have these two different ways of violating sigma 1 induction.
Mm-hmm. All right.
Okay? So you get many automorphisms of the first order part because you have these isomorphisms between the second order parts. And secondly, whatever you do to expand a model of RC 0 star plus not I sigma 1, lives within a model of weak Kőnig's lemma, because you could use Smith-Simpson to expand it to a model of weak Kőnig's lemma. And it lives in a model of weak Kőnig's lemma, but all of these guys are isomorphic. So they're the same up to isomorphism. So in some sense, you can't really expand a model of B sigma 1 plus not I sigma 1 that much, because all the things that you can expand by, they live in this one single model of a weak Kőnig's lemma that you have. Okay, so that kind of, to me, explains both of these phenomena that we observed. This is just a loose comment. I feel that in some sense, this result that I'm mentioning today relates to various results on the existence of automorphisms of the first order structure, kind of like Tanaka's self-embedding theorem relates to Friedman's theorem, right? I mean, Friedman's theorem was about self-embeddings of first order models, and then Tanaka generalized it to second order self-embeddings of weak Kőnig's lemma models. And this kind of looks a little bit similar in a way, although it's in this unusual setting where you have to fail induction to make it hold. Yeah, I guess this is the seminar where I can try to say something about the proof. The proof isn't that hard, I think. To me, the hardest part was coming up with the statement, actually believing that it might be true. So I'll give you a very rough sketch of the proof. Please don't be too technical in asking me questions. As I said, I've listened to too many oral exams today. Let's take these two models, say whatever they are, whatever these names for the second order universes satisfying Kőnig's lemma are. We're going to do a back and forth argument, as you can imagine. There's going to be a first order and a second order step because we're adding both first and second order elements to the domains and ranges of our isomorphism. We can assume, essentially without loss of generality, that the set A, the common failure of induction is already this sort of sparse set that's indexed by a sigma 1 cut. Because if it's not, then there's going to be such a set that's delta 1 definable in A. And well, you could put A in the tuple at the start to make sure it's preserved as well. So the isomorphism, did I say this? Oh, perhaps I missed it in the statement of the theorem. The isomorphism will require, or we may require the isomorphism to fix A as a set setwise. So f of A will be A for isomorphism. We may require that. Anyway, we may assume with also generality that A itself is this sparse cofinal set that you get by failure of induction, that it's indexed by a cut I, that this cut is a proper cut that's closed under X. We can always take this sort of cut indexing a sparse infinite set. And we can also cut off some elements. This will not violate the closure under X because you start with a cut closed under X. So we can also assume that the smallest element of this set A is above the cut. So the picture can be like that. At each step in the argument, we're going to have finite tuples, little r and big R in the domain, first order and second order elements of the partial isomorphism that we have, and little as big as in the range. At first, the little tuples, the first order tuples are, let's say, empty. Unless, of course, you want to fix some particular elements of the model, you may. The second order tuples, let them just consist of this set A. So A is going to be mapped to A. The inductive invariant that we keep is as follows. There exists an element B above this cut I indexing our set A. And there exists a very, very small number, so small that it's almost standard, so let's call it epsilon. There exists a non-standard number epsilon with the following properties. For any I in this cut, and for any bounded formula with parameter, with Gödel number below epsilon, so a very small bounded formula, almost standard, and any parameter below this bound B, which is somewhere above the cut J, any formula, any such formula with Gödel number below epsilon is true about AI, the eighth element of our set, this parameter J, and our tuple from the domain of the partial isomorphism, if and only if it's true about Aij and the tuple from the range. Of course, this is expressed using a truth definition for bounded formulas. So that's the point. And along the way, during the construction, you add stuff to the tuples naturally, and you decrease this bound on the parameters for which these formulas are equivalent with the R's and the S's, and you decrease the Gödel numbers of the formulas that you consider. Okay, so that's the overall picture. I'm afraid that this is the last picture of the talk. The rest is text only. So let me say something about the proofs, the steps. So the first order step, there's a symmetry between domain and range here, so we can assume that we're adding a new element to the domain, let's say R star, and we need to find a corresponding first order element in the range. Let's call it S star. So we're looking for S star. Now, crucially, the set A is cofinal in the model, right? So wherever R star lives, there is going to be an index I0 such that R star lives below AI0. Okay. Now, let's decrease our requirements on what things we want to be equivalent in the next step a little bit. So let's make the new B, let's say B prime. I think log suffices. Maybe you need log in both cases, but I wouldn't worry about that too much. And let's decrease the Gödel numbers that we care about, epsilon, by double exponentially as well. So let's make epsilon prime be log epsilon. Again, log if it's really needed. And now there is going to be an element J star below, I guess, this log of the previous bound in the parameters B, with the property that the intersection of the finite set, the M finite set coded by J star with This should be a Cartesian product. I apologize. Only the first intersection should be an intersection. These guys should be Cartesian products. So with the cut I times, the initial segment 0 up to B prime times the initial segment 0 up to E prime, that it consists of those indices I in the cut I, those parameters J, and those formulas delta, for which delta holds of AI, J, and the tuple domain extended by R star. Such a thing exists. It's not completely obvious that it exists. It's not, we're not coding a delta 1 set, and we have just delta 1 induction, but we're coding something close enough to a delta 1 set that this is going to exist by the so-called Chong-Morad coding lemma. This is something I mentioned in the previous talk I gave here at MOPA. So for this R star and this J that kind of codes the truth about R star, the following statement is true. Let's fix an I in an index of an element in our set A. Let's assume this I is big enough so that things don't get messy for the reason of I being too small. The following statement is true. There is a Y smaller than AI0. This Y is going to be R star, such that for every I prime below I, and for every J below B prime, so this is our decreased requirement on the parameters. And then we want to say for every formula delta with Gödel number below epsilon prime, this is said, this can be stated as a true definition applied to a non-standard but relatively small conjunction. So for every formula delta with Gödel number below epsilon prime, delta holds of AI prime, J, R bar, this Y, which is going to be R star and capital R bar, exactly if the index of the element, the parameter below B prime, and we plug in the numeral for delta, if this belongs to J star. This is simply true. This states the existence of R star, and it says that J star codes the correct set. And if you think about this closely enough, you can apply the inductive assumption to this to conclude that the same thing has to be true about the tuple of S's in place of the tuple of the R's. Okay, so for every I, there is going to be an element below AI0, which behaves as R star does with respect to the S's. We consider equivalence with respect to a sufficiently large number of formulas. But up to elements in this sparse infinite set A, indexed with indices up to I. Okay, so we get the same formula here, but with S's instead of R's for every index I in our cut capital I. And at this point, you apply sigma 1 collection to figure out that there is going to be one single element Y, AI0, which works for the S's and for all the I's. This is a typical use of sigma 1 collection. If for every Y below AI0, there would be a bad I, then you could bound the I's. And then you would get a counterexample to this. Okay, so that's how collection matters in this argument. The second order step is more or less similar, except that now we have a second order object being added to the domain, say capital R star. We need a second order corresponding element in the range of the isomorphism. That's S star. So instead of having statements stating the existence of elements, you now state the existence of finite sets that approximate this R star. these guys transfer to the existence of finite sets approximating the S star by inductive assumption. And finally, to get a good enough full infinite set S star from these finite approximations, that's where you apply weak Kőnig's lemma. So weak Kőnig's lemma is to the second order step exactly as sigma 1 collection is to the first order step. And you work out the details, and that's it. Okay, so that's the proof. So I guess for the rest of the talk, I wanted to talk a little bit about consequences, and then I'll have a loose related problem at the very end for all of you. So here's the first consequence. In this context, weak Kőnig's lemma star and sigma 1 induction fails. The analytic hierarchy collapses to the arithmetical hierarchy. Incredible as that may sound, it did to us at first. So in general, if you violate sigma 1 induction with a second order parameter A, then every second order formula is equivalent to a first order formula with A as a second order parameter. So as the violation of sigma 1 induction is light phase, you literally get the analytic hierarchy collapsing to the arithmetical hierarchy. I sketch a proof of this very, very briefly. The point is that there is a way of, given this set A violating induction, you can describe, there's a single tree T such that any path in this tree T will code, in the sense of countable coded model, will code a model of weak Kőnig's lemma that contains the set A as one of its elements. There is a standard arithmetically definable forcing notion that adds paths to this tree. And you can check that any formula, any second order formula eta will be true in a model of weak Kőnig's lemma if and only if it's forced to be true in this forcing notion. And describing this is always going to be arithmetical. So that's how you get this collapse of the analytic to the arithmetical hierarchy. Another corollary, which was actually, we had this quite a bit earlier than we got the isomorphism theorem, namely, we get something approximating a negative answer to Towser's question, namely, there's a maximal pi11 conservative pi12 theory over RC0, plus you have to explicitly add sigma 1, negated sigma 1 induction. So a sentence, a pi12 sentence is pi11 conservative over RC0 star plus not induction if it's provable from weak Kőnig's lemma plus not induction. The argument here is that in one direction, if weak Kőnig's lemma plus not induction proves the sentence C, then it's definitely going to be conservative by Smith-Simpson. In the other direction, if weak Kőnig's lemma plus I sigma 1 does not prove C, then the sentence saying that C isn't forced is going to be consistent with RC0, but it's going to be provable from RC0 plus C. Therefore, from weak Kőnig's lemma plus RC0 plus C, and if C were pi11 conservative, then weak Kőnig's lemma plus C would also be conservative. Sorry for the slightly messy explanation, perhaps. This only applies to pi12 sentences because at one point in the more complicated direction, you need an amalgamation argument to show that if C is pi11 conservative, then weak Kőnig's lemma plus C is also pi11 conservative. So this doesn't work. It's actually false for sigma 1-2 sentences in general. Not weak Kőnig's lemma as an example that would violate this criterion. So this is a criterion of conservativity over collection and not induction. There's another corollary that says that the low basis theorem fails very, very badly over these models of collection, not induction, namely because each model of weak Kőnig's lemma contains a coded submodel of weak Kőnig's lemma, so a smaller one, and they are actually going to be isomorphic if they contain this common induction, example to sigma 1 induction. That tells you that any set coding this coded submodel of weak Kőnig's lemma cannot be arithmetically definable, because otherwise that would violate the existence of the isomorphism. So the low basis theorem fails very, very badly here. If you have a second order universe satisfying weak Kőnig's lemma over failure of induction, then it contains a set that not only isn't low, it can't even be arithmetical. It's not definable in the first order part of the model. Yeah, a comment on generalizing this to higher levels of the arithmetical hierarchy. Well, there is this principle that we call delta n or delta 0n weak Kőnig's lemma, which relativizes both the instances and the solutions, so both the for all and the exists quantifier in weak Kőnig's lemma, to delta n definable sets. We're living in a world with just delta 1 comprehension, so a delta n set might not be a set in the sense of second order objects. So this principle says every infinite binary delta entry has a path that might not be a set, but it's going to be a delta n set. So this principle is true, this delta n weak Kőnig's lemma is true in a model of second order arithmetic, if and only if the delta n definable sets of that model satisfy weak Kőnig's lemma star. Okay, that's exactly designed for the statement to work. So basically what this says, this principle actually proves sigma n collection. What this principle, what our result relativized says that if you have two different models of delta n weak Kőnig's lemma and sigma n collection, then they're, so to speak, delta n closures. So they're delta n definable universes, they're going to be isomorphic if they violate sigma n induction in both cases. Okay. This delta n, this fact is worth knowing, that this isomorphism theorem for models of delta n weak Kőnig's lemma, because this principle is pi11 conservative over C0 plus B sigma. So it's actually a meaningful and not particularly strong principle. The most interesting case, as mentioned, is where n equals 2. So models of sigma 2 collection and not sigma n, sigma 2 collection, not sigma 2 induction. Here it's known, this was proved by a eternal preprint, like never published paper, or at least not published so far, paper of David Belanger. He showed that this principle delta 2 weak Kőnig's lemma is equivalent to a different principle. It's a consequence of Ramsey's theorem, in fact, known as the cohesiveness principle, COH. This principle says the following thing: if you were given a sequence of sets, x0, x1, x2, and so on, then there's one infinite set that uniformly splits these guys into small and large. So it's like a largeness notion for these sets, or in sort of, I don't know, ultra filter or something like that for this particular family. Namely, there's an infinite set C that for each n is either almost contained, up to finitely many elements in the set xn or in its complement. So that's the cohesiveness principle, and it has been known that delta 2 weak Kőnig's lemma is exactly this thing. So that tells us that if you have two models of weak Kőnig of RC0 plus sigma 2 collection plus co, and they contain a common violation, like a common parameter that witnesses a violation of sigma 2 induction. Now we can relativize the whole picture to zero jump, apply our theorem, And what this tells us is that these models, MX and MW of this cohesiveness principle, they might not be isomorphic themselves, but their delta to definable universes will be. Okay, so just around the corner, there are these sets, models that just add a little bit of stuff to X and to W, and these guys are going to be isomorphic. So that's the analog or the relativization of our theorem to n equals 2. That's what you actually get by these methods. So what does the generalization give you? Firstly, maybe we won't go through this in detail, but again, this almost negative solution to Towser's problem gets generalized to higher n. So for each n, the set of pi1, 2 sentences that are pi1, 1 conservative over sigma in collection and not sigma in induction, that's an RE set. That's actually a consistent recursively axiomatized theory. It was known to be consistent, so the only thing is that it is RE, and there is a criterion. So a sentence is pi1, 2 sentence is pi1, 1 conservative over this theory. If this delta n with Kőnig's lemma, this would be COH in the case n equals 2, proves a somewhat different sentence, that it doesn't prove for all x's exists y, but it says that for all x, there exists something that might not be a set itself, but is in some sense kind of low or non-complicated, that would witness this formula, this arithmetical part of the pi1, 2 statement. So you don't quite get provability of in delta n with Kőnig's lemma of these pi1, 1 conservative pi1, 2 statements, but you get some approximation on that, and that's the RE criterion for conservativity. There are particular consequences for Ramsey's theorem. So what we're basically sure of, because we've written that down and checked, is that using some particular features of Ramsey's theorem, that it's known to not add any new arithmetical or pi1, 1 consequences of I sigma 2. It proves B sigma 2, and it proves the cohesiveness principle. So if you work with that, what you get is that one of these major outstanding questions about Ramsey's theorem in reverse mathematics, namely whether it is pi1, 1 conservative over B sigma 2, you can write down a particular pi1, 1 sentence. It's actually generalized pi5, meaning for all, where these for all quantifiers might be second order, then a sigma 4 thing. And this sentence is provable in Ramsey, and it's provable in collection if and only if the first order consequences of Ramsey, or pi1, 1 consequences of Ramsey, actually are collection. I think we believe, but this has to be checked. I mean, too many of us are dealing with exam sessions or analogous things, but we now believe that actually you can use this construction to axiomatize the arithmetical consequences of more or less any pi1, 2 statement over sigma and collection and not sigma and induction. In the particular case of Ramsey, which, as mentioned, doesn't prove anything beyond I sigma 2 and proves B sigma 2, this would give an axiomatization of the arithmetical consequences of Ramsey's theorem, although having this axiomatization does not settle the question whether it's equivalent to B sigma 2. It's going to be an arithmetical theory, which we're probably going to be able to write down, but there's some additional combinatorics to be done to decide whether that's by sigma 2, and I guess the jury is still out on whether that's just around the corner or still very hard, because there is essentially novel combinatorics to be done. Okay, one final comment. I guess I'm probably approaching the end. I guess I could squeeze in this short discussion. So what about Towser's original problem? The problem was, is it pi2 complete to decide, given the pi1, 2 sentence, whether the pi1, 2 sentence is pi1, 1 conservative over sigma in collection for some fixed natural number n? the answer turns out to be positive. So I would say the more interesting, as it turns out, version of Towser's question has a negative answer where you explicitly add not induction here. But if you just take the original question, we have conservativity over collection, but that has a positive answer. Let me mention what goes into the proof. This is relatively easy. It's basically an observation. There is this thing called the cardinality principle, C sigma n, which says it's a very weak form of the pigeonhole principle. It says that for sigma n formulas, it says that for any natural number x, there is no sigma n injection from the entirety of the natural numbers, from the whole number universe into x. So it's a very, very weak PHP. And there are two interesting things about it. Namely, on the one hand, whenever you have a model of a certain amount of induction, you can expand it to a model that has the same amount of induction. This is always about countable models, sorry. Let's say it's sigma n induction, that has a delta n plus 1 bijection between the whole universe and the standard cut. So you can violate this principle C sigma n plus 1, let's say, very badly, and still keep sigma in induction if you had it. This is essentially a consequence of Towser's theorem, but I guess there's a separate construction known earlier by Groszek and Slayman. And on the other hand, if you have these models of collection and not induction, then they can never ever falsify a cardinality principle for whatever level of the arithmetical hierarchy of definability. So models of collection and induction simply satisfy these cardinality principles. There's an isomorphism argument for this. There's a kappa-like model for singular kappa argument for this. Anyhow, this never happens. And using these two properties, I'll skip the details. You can write down a sentence. This is sketched for n equals 1 here. That basically, given a pi2 statement, you can write down a sigma 1 sentence that will be conservative over collection if and only if the pi2 statement was true in the standard natural numbers. But this sigma 1 sentence, I won't get into the details, I guess, but it's a disjunction, and the first disjunct says not induction. So models of collection, not induction, don't really do any work here. Because they will always satisfy this sigma 1 sentence simply because it has a disjunct saying that not induction is enough to satisfy it. So basically all of the work gets done over these models of induction. And now we know why, because for models of collection, not induction, actually conservativity is not pi2 complete. That's it. I have one question. That's almost it. I have one question that's loosely related to this stuff, but I think it's interesting. And it's not clear that our methods can do anything about it. Maybe they can, but I think it's interesting and I would like to sell this. So we are basically studying this theory. I think it was defined, the notation was defined by K. He might have been the first to study it. But basically says the first level at which the hierarchy of arithmetical induction fails is an induction level. So it never, the last one which holds is a collection, right? So if at all induction fails, then there is some n such that delta in induction holds, but sigma in induction fails. That's IB, which I guess means I implies B, induction implies collection. There are two natural ways, at least, of relativizing this to a second order context. Either you can say that relative to every x, IB holds. So yeah, so that's what we call a strong relativization. Maybe that's the more natural one. There is another one that's also kind of natural that just says that the first level relative to any parameters whatsoever where induction fails is going to be an I level and not a B level. So if sigma n induction holds for relative to all sets, then sigma n plus 1 collection also holds relative to all sets, but there might be a set relative to which maybe sigma n plus 7 induction fails, and sigma sigma 7 n plus 7 induction holds, and sigma 8 n plus 8 collection fails. So we have this problem that we have not been able to solve so far, whether these two relativizations are actually equivalent. It would seem kind of surprising, but we've gotten used to surprises in this area. So here's a model theoretical reformulation. I think I stated one that's essentially equivalent, or almost equivalent at least. Basically, is it ever possible to take a model, possibly already with some parameter, that satisfies induction and violates the next collection, and expand it to a model that violates, that satisfies a lesser amount of collection but violates induction? Okay, so is it ever possible to go from a model of I and not B to a model of B and not I, of course for a lower parameter here, for a lower level of the arithmetical hierarchy here by expanding? If you exchange the roles of I and B, then the answer is definitely yes. It's definitely possible to go from B and not I, for say B sigma, a model of B sigma 2 and not I sigma 2, to a model of I sigma 1 and not B sigma 2 by expanding. But in this direction, we don't know. It seems like a difficult problem. If anybody, if any of you have any comments on this, we're interested, because it looks like a really interesting question to ask. Thanks. Sorry for going a bit over time.
Leszek, thank you very much. Now we clap. I clapped. And are there any questions?
I have a quick question. Can you hear me?
Yeah, I do. Hi.
Oh, very good. I wasn't sure. This nice result that you have, that we have an instance of a conservativity problem being semi-decidable.
Right.
Are there other instances in the literature of such an interesting phenomena?
I think Lawrence asked about this, and we didn't have any good idea. And you want something natural, and inconsistency doesn't count, right? The inconsistent theory.
Right. Yes.
I am not aware of it. I am not a great expert on, general studies of recursion theoretic properties of conservativity questions, but an initial guess, yeah. So sometimes I think we had this for a smaller. Keita pointed this out, that if you considered conservativity, for instance, relative to a very, very restrictive, over say I sigma 1, but to a very, very restricted class of pi 1, 1 sentences. So you just can't care about conservativity for those sentences. I guess just for all sets exists a number. Then weak Kőnig's lemma tells you that exists a set that for all numbers is actually a pi one thing. It's arithmetical. So therefore, I guess the maximal, I have to state this correctly. You can cook up a situation in which weak Kőnig's lemma will be maximal conservative relative to these principles. I'd have to recall what it is, but I like her example better. And yeah, I'm not aware of others. So I think you could possibly present examples in which a somewhat stronger theory is required to observe a collapse of the formula hierarchy that a weaker theory cannot observe. You could possibly present this sort of situation as a case where conservativity is going to be sigma 1 or something. but I don't know of any good examples, at least. Well, this one is also kind of like that. I mean, what's happening here, the reason that this maximality happens is that analytic formulas turn out to be arithmetical. So in some sense, this is also the reason behind that.
Yeah, I was curious in particular, and you answered, I think, my question, whether this phenomenon had occurred in other parts of reverse mathematics that you're familiar with, and it sounds like the answer is no.
So the answer is you could sort of write this phenomenon possibly into some situations in which this was not observed, but it was not that interesting. So that's how I would probably look at it.
I guess what you're saying is that if one were to draw the target around the arrow, one would be able to get that.
Yeah, that's what I would say. Right, that's what I would say. But here, this was a legitimately asked question about the complexity of the conservativity problem, and yeah, I mean, the original question gets an, I would say, somewhat uninteresting positive answer. Maybe not completely devoid of interest, but not very surprising. And all along, we were expecting this to have a positive answer for some, relatively mundane reason. And on the other hand, there is a possibly more interesting way of phrasing the question that turns out to be unexpectedly no, because yeah, it's semi-decidable, as you said.
I see that Ken McAloon has a question.
Yeah, hi. Yeah, it's very exciting. Work that connects complexity theory with model theory. And here you connect, listen, that's the pi 1, 2, that's the questions about pi 1, 1 sets, because a pi 1, 2 question, and that's equivalent when you have here, which is something as pi 1, 2 complete question. Right now,
the completeness is pi 2. It's arithmetic.
Pi 2. Ah, right. So does that scale up as you could pi 1, 1 and pi 2? Can you scale up to pi 3, pi 4? That's a formal question, just driven by the notation.
Well, right. I guess you would have to come up with some sort of something like conservativity modulo truth or something like that. And possibly it is the case, but I haven't thought about it at all, right? I mean, you'd have to, a conservativity problem is always going to be pi 2 at the worst for recursively axiomatized theories. So basically, you have to be willing to accept non-recursively axiomatized theories. And I guess the natural thing to do would be to add pi 1 truth to what you're doing, right? And then consider a slightly larger amount of induction in your theories, and yeah, that's possible. I wouldn't rule it out.
Thank you.
Okay. Any more questions? Well, if not, then let's thank Leszek again. Thank you, Leszek.
Oh, thanks.
Thank you.
An interesting talk. And I hope to see all of you next week. Mateusz Wełyk will talk about truth theories and Tarski's boundary. So that's next Tuesday. Okay, see you then.